Today we're going to talk about yet another way that we can solve first-order differential equations. Namely, we're going to talk about exact equations. Now, exact equations may be separable or linear, and we could use those techniques, but there's another way that we can solve them as well that might be preferable to separating variables or using an integrating factor. So let's take a look at exact equations. To begin our exploration of exact equations, we want to take a look at the first order differential equation, y dx plus x dy equals 0. It's true, this equation is in fact separable and linear, so we have techniques available to us to solve it. However, we can save ourselves a lot of work if we recognize it as the derivative of the product x times y. That's the general idea we're going to be working with today, is this use of the product rule to make our lives a little bit easier in solving our differential equations. So we're first going to recall that the differential of z equals f of xy is dz equals the partial derivative with respect to x dx plus the partial derivative with respect to y dy. Now, if you haven't had Calculus 3 multivariable calculus, you might not be familiar with this partial derivative notation. What this is doing is it's taking the derivative with respect to x while we're treating y as a constant, and then taking the derivative with respect to y, treating x as a constant, depending whether we're taking the partial with respect to x or the partial with respect to y, respectively. So we're just focusing on a single variable at a time. That's really the important thing. So the definition of an exact equation. We have a differential expression m of xy dx plus n of xy dy. This is considered an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy defined in R. A first-order differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be an exact equation if the expression on the left-hand side is an exact differential. So now we need to be able to identify an exact differential. So we're going to let m of xy and n of xy be continuous and have continuous first partial derivatives in a rectangular region R defined by a is less than x less than b, c is less than y is less than d. Then a necessary and sufficient condition that m of xy dx plus n of xy dy be an exact differential is if we take the partial derivative of m with respect to y and the partial derivative of n with respect to x, and those two partial derivatives are equal to each other. So now we're ready to consider a method of solution. The first thing we have to do is check that a differential is in fact an exact differential by checking that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. After we've determined this, we take m of xy and we integrate it with respect to x, holding y constant. This results in f of xy equals the integral of m of xy dx plus g of y. G of y is our constant that we're adding. Now, it's a function in y because we're considering y a constant through this. So our constant can be more than just an integer or a real number. It can be more than some number. It can actually be a function in y. So g of y is our constant of integration here. The next step that we're going to take is working towards finding what g of y actually is. What is that constant of integration? We want to solve for it. So to do that, we're going to differentiate with respect to y, and we're going to assume that the partial derivative of f with respect to y is equal to n of xy. So we'll take the partial derivative of f with respect to y. This will be the partial derivative of our integral of mxy dx with respect to y plus our derivative of g of y. And we're going to set that equal to n of xy. Once we've done this, we're going to solve for g prime of y. So we're going to solve for that first derivative of y that's nested in there. So we'll get g prime of y equals n of xy minus the partial derivative with respect to y of the integral of m of xy dx. Now, to finish solving for g of y, we need to integrate. So we'll integrate with respect to y and substitute the result in for g of y in our f of x equation that we obtained in step number 2. The implicit form of the solution is found by setting whatever we get for f of xy after we've substituted in for g of y equal to c. And to obtain the explicit form of the solution, we need to solve for y. So now let's take a look at some examples. Let's first consider the differential equation 2xy dx plus the quantity x squared minus 1 dy equals 0. Now this is set up in the form that I am looking for, m of xy dx plus n of xy dy equals 0. So I'm ready to move on to my method of solution. So the first thing I have to do is check to see that this is an exact equation. To do so, I'm going to check that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So first I'm going to identify this is m of xy, and this is n of xy. So my first step, I need to take the partial derivative of m and the partial derivative of n. So to take the partial derivative of m with respect to y, I'm first going to look at my expression, that is my m of xy expression, and I'm going to consider it through a lens where I'm looking at y as a variable and x as just a constant. So in this case, I have basically a constant of 2x times my variable y. Well, the derivative of a constant times y is just that constant. So this is going to equal 2x. Similarly, I can take the partial derivative of n with respect to x, and I'm going to treat x like a variable now, and any y's that appear as constants. Now in n of xy, that expression is x squared minus 1. There are no y's, so I don't even need to worry about it. So I'm just going to differentiate this with respect to x, and I'll get 2x. Since the partial derivative of m with respect to y and the partial derivative of n with respect to x are both 2x, then I know that this is an exact equation, and I can move on with my method of solution. So the first thing I need to do is integrate m of xy with respect to x while holding y constant. So that'll look like f of xy equals the integral of 2xy dx plus g of y. And when I take that integral, I'll get x squared y plus g of y. Now I'm ready to move on to the next step of my method of solution, namely where I'm trying to identify what g of y is. So I'm going to differentiate with respect to y and assume that the partial derivative of f with respect to y is equal to n of xy. So what that will look like is the partial derivative of f with respect to y equals the partial derivative of x squared y with respect to y plus g prime of y equals n of xy. So taking the partial derivative of x squared y with respect to y, I'm going to treat y as a variable and x as a constant and take the derivative of that expression. So that will look like simply x squared. Now, plus g prime of y stay the same, and I'm going to go on and plug in x squared minus 1 for n of xy. Doing so, I end up with x squared plus g prime of y equals x squared minus 1. And now I'm ready for the next step in my method of solution, namely solving for g prime of y. Solving for g prime of y is as simple as subtracting x squared from both sides. This leaves me with g prime of y equals -1. Now, to find g of y, I simply need to integrate with respect to y. So I'll be taking the integral of g prime of y dy, and it'll equal the integral of -1 dy. This will give me that g of y equals -y. Now, I need to substitute -y in for g of y to my f of xy equation that I had up here. So, doing that substitution, I get f of xy equals x squared y minus y. So, the implicit form of the solution is f of xy equals c. So, I can find that simply by setting x squared y minus y equal to c. And I can solve for the explicit solution by solving this for y. That'll require factoring out a y and then dividing by whatever is remaining. And doing so gives me an explicit solution of y equals c divided by x squared minus 1. Consequently, I can see that this will be defined on any interval that doesn't contain +1 or -1. Those are the two values that would result in a 0 in my denominator, and consequently a non-existent solution. Now in this example, no initial value was presented. However, if it was, I could find the exact value of c by simply substituting in the initial values for x and y and solving for c. As long as x was not plus or minus 1, then I would have a value of c, and we could obtain a particular solution. There are times that you'll have an equation that is not an exact equation. However, you can make it be an exact equation through the use of an integrating factor, similar to how we used integrating factors with linear equations. So let's take a look at an example of a non-exact differential equation and see how we can make it an exact differential equation so that we can use our solution process on it. So let's consider the example xy dx plus the quantity 2x squared plus 3y squared minus 20 dy equals 0. The first thing that we do is we look at m of xy and n of xy, and we'll check to see if this is an exact equation. So xy is m of xy. 2x squared plus 3y squared is minus 20 is n of xy. So remember, the first thing that we need to look at is the partial derivative of m with respect to y and the partial derivative of n with respect to x. When I take the partial derivative of m with respect to y, simply get x. However, when I take the partial derivative of n with respect to x, I get 4x from the first term, and then everything else is 0 since they're all treated as constants. But x does not equal 4x, so this is not an exact equation, and I can't use my exact solution technique on it. So when this happens, we have a couple of quotients that we can go to, and if they satisfy certain criteria, then we can make use of an integrating factor to turn this into an exact equation. So we can use our exact equation solution technique on it. So the two quotients that we consider is quotient 1 is m sub x minus n sub x. That's the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n. If that is a function of x alone, then we use an integrating factor mu of x equals e to the integral of that quotient dx. Now, if that quotient is not a function of x alone, then we move on to quotient 2. Quotient 2 says n sub x minus m sub y divided by m. That is the partial derivative of n with respect to x minus the partial derivative of m with respect to y divided by m is a function of y alone. Then we use an integrating factor of mu of y equals e to the integral of that quotient dy. So let's check and see if either of these quotients works for our example. So checking quotient 1, we have the partial derivative of m with respect to y. We already know that that is x. The partial derivative of n with respect to x, we already know that that is 4x. And we know that n is 2x squared plus 3y squared minus 20. Now, this will not be a function of x alone because there is a y in it, and I have no way of that y squared ever canceling with anything to be eliminated. So this quotient is not a function of x alone. So this is not going to work. So let's move on to quotient 2. In quotient 2, I'll be taking the partial derivative of n with respect to x, so 4x, and subtracting from that the partial derivative of m with respect to y, so I'm subtracting x, and I'm dividing by m, so m was xy. Now I can simplify this, so I have 4x minus x is 3x divided by xy. Every term has an x in it, so this is equal to 3 over y. Now this is a function of y alone, so this works. So I'm going to be using an integrating factor, mu of y equals e to the integral of 3 over y dy. So having an integral in my integrating factor is not necessarily a great thing, so let's go on and take that integral, and we'll get e to the 3 natural log of y, which we know is equal to e the natural log of y cubed by log rules. And then we know e raised to a natural log results in just whatever is in the natural log. So this is all equal to y cubed. So our integrating factor is going to be y cubed. So now what we're going to do is we're going to multiply our original differential equation by y cubed. Every term in it will multiply by y cubed. So just to remember, our differential equation was xy dx plus the quantity 2x squared plus 3xy minus 20 dy equals 0. So we'll multiply every term by y cubed. And we'll get xy to the 4th dx plus the quantity 2x squared y cubed plus 3y to the 5th minus 20y to the 3rd dy equals 0. Now, this may seem like we have made this a whole lot worse to work with. However, let's take a look at those partial derivatives of m with respect to y and n with respect to x now that we've incorporated our integrating factor. So taking the partial derivative of m with respect to y gives me 4x y to the 3rd. And taking the partial derivative of n with respect to x gives me 4x y to the 3rd from the first term. And there are no x's in the other terms, so the other two terms are like constants and they add 0 to my derivative. So I now have the partial derivative of m with respect to y and the partial derivative of n with respect to x are equal to each other. So this is now an exact equation, and I could go through the same process, that same method of solution that I went through in the previous example to arrive at an answer.